Hello and welcome to Remcom's webinar on matching network design. I am Jeff Barney, a product marketing manager, and I will be walking you through this demonstration today. In particular, I am interested in showing where full-wave matching circuit optimization fits into the workflow. This is a relatively new technology that is unique to XF, so I want to show how this is an extension of what you are currently doing. XF has been developed for RF engineers who design antennas, so it provides the tools necessary to design a matched antenna. This is today's agenda, and we are basically going to cover each of the steps in the workflow. So starting with an unmatched antenna, we're going to talk about how you can bring the model into XF, either as an imported CAD model or by creating it directly within the modeling package that we have. Once we have that matched antenna, we're going to run an FDTD simulation and compute S parameters and efficiency for it. And so that's basically the first step where we characterize the unmatched antenna. Once we have that characterization, we're going to synthesize a matching network topology using Optenni Lab. Optenni Lab is a third-party software package that XF integrates with. Once we have the topology, we're then going to move on to the physical layout, and here's where we take and actually physically lay it out on the board with copper traces and connect it into the antenna. The final step is where we're going to determine the final component values. So we want to know what are the specific values for the inductors and the capacitors that provide the match that we're interested in. And here we're going to be looking at a dual band antenna. So we're going to be looking at the GPS band in the lower band, and then the higher band, it's going to be the Bluetooth band. I'm expecting roughly 25 minutes for this demo, and there's going to be time for questions at the end. And actually, you can enter questions at any point in time, and then I'll just get to them whenever we get to the end. So let's go ahead and get started. Analyzing an unmatched antenna starts with getting the 3D model into XF. You can do that by either importing a CAD model, or you can create the model directly within XF using the modeling tools that we have. For CAD import, XF supports multiple different formats, and it allows you to bring in files that were generated in SolidWorks or Pro Engineer or another modeling package, and that might be bringing in the antenna, but then also the housing around it, any kind of plastic pieces or displays that's associated with it. It could also be an antenna that was on a printed circuit board, so you may be using a layout tool from Cadence or Mentor Graphics, and you have the antenna printed on one layer of the PCB, and then that can also be imported as an ODB++ file. Once you have this model within XF, you're then going to want to analyze it. You're going to want to run a simulation, and what you're going to want from that is S parameters or efficiency. Here the graph is showing how we've parameterized part of the antenna, and we've run a parameter sweep and we've calculated S11 for the different antenna lengths. If we look at that in the software, I'll be using this model to show the matching network design workflow in XF. This is a GPS Bluetooth antenna. It's located in the corner of the PCB. The PCB is about the size that you would find in a mobile device. And we're going to be looking at designing a matching network to connect this antenna down into ground. All of this was created directly within the modeling tools of XF, and so I just want to walk you through how that was done. Here on the left in our parts list, we can see that we have the antenna, and if we expand the antenna, we can see that it is made up of multiple operations. So XF has this concept of feature-based modeling, where we start out with a fairly simple structure, and then we add modifications to it, thereby making it more complex. So here we started out with a simple extrude. If I double click on it, I can hide my geometry, and I'll hide this construction grid. We can zoom in and we can see that this antenna started out as just a simple cross-section with one rectangle is the main outer edge. We have another rectangle in the middle that's generating the slot, and then we have a hole that's also being created. The green down here is a constraint, and this is showing that we have constrained the length of this antenna to being 21.25 millimeters. And if I open up our parameters window, we can see that this is actually a parameter that's been defined. And so we have an antenna length parameter that we can then change or perform a parameter sweep on later on. Once I have this cross section, I can then specify a distance that I would like to extrude it. So here I was just doing a very small distance just to give the metal some thickness. From there, we're going to want to take those squared off edges and we're going to want to round them. So we've done that with 3 different blending operations. The first one is going to put edges or rounded edges on the inside of this slot. So we've gone through and selected the 4 corners, specified a radius of 0.4 millimeters, and now we have rounded edges. We've done that 2 more times. So we rounded the edge on this edge, or on this side of the antenna, in the same way, just with a different radius. And then we also blended these edges on this side with also another larger radius. Once we have that cross-section defined and then the edges blended, well, then we wanted to add some bends. And so the first bend was going to be bending the top and taking this flat object here and then bending it around this certain radius. If we look at the preview associated with that, we can then see how that bend is applied. And when we add the second bend, we can see that that bend was applied here along this line, and we have the bent antenna. If we come back to look at the parameters and how it's applied, we can come back to our parameters window, change this, let's say to 25 millimeters, and when I hit apply, you'll see that this antenna gets longer. And that's because we're going back and modifying the original extrude, and that modification propagates through all of the rest of the modifications that we have. Once the CAD model is in place, we then need to make sure that our materials are defined. So we have material definitions for copper and for the dielectric. We also have a source being applied here. So this is just a 50 ohm voltage source that's connecting the antenna down to ground through this via. And so now we're ready to run a simulation. We come to the simulations window. I want to create an FDTD simulation, and this is where we're just going to do a full wave analysis and calculate S parameters and efficiency for this structure. We've also, I've run it ahead of time and I did it with defining a parameter sweep. So we're going to be looking at the effect of changing the antenna length from 20 to 30 millimeters. This was run on a cluster that we have, so we're taking advantage of GPU acceleration. And once the simulations are finished, we can come into the results and we can go ahead and load the S parameters for that unmatched feed. Let's go ahead and look at all of them in the frequency domain, broadband frequency domain. And we can see here the effect of those parameter sweeps. So the purple or the magenta line here is for 30 millimeters, and this dark blue is for 20 millimeters. So with that, we have analyzed our unmatched antenna, and we've calculated S11 for it. The next step in the workflow is going to be synthesizing a matching network topology. And here we're going to want to take that S11 data and that efficiency data, and we're going to want to export it into Optenni Lab. Again, Optenni Lab is a third-party software package that is available from Optenni, and it is a matching network topology synthesis tool. So it will take S11 in efficiency, and it will generate a matching network topology and predict the match based on that data and based on that topology. So if we show how that's done in the software, again, we'll come back to our result browser, and this time we're going to want to select both our efficiency and our S parameter data. I ran this for a specific antenna length of 21.25 millimeters, and so I'll select the system efficiency and the S parameter results, and I'm just going to go ahead and right-click, export it to Optenni Lab. What that's going to do is write the input files necessary for Optenni Lab, and then it's going to open Optenni Lab immediately. Here it's just checking for a license, and now we have our data within Optenni Lab. We can verify it here by looking at S parameters. So this is the S parameter result that we calculated within XF. We also have the termination impedance. So this is just showing us that we had a 50 ohm voltage source. And then finally we have efficiency data. So here I collected efficiency data in the GPS band and then also efficiency data in the Bluetooth band. Optenni connects the dots, and so that's why we have this long straight blue line even though there's no data in the middle. So the first step with Optenni is to come in and define the bands that we're interested in analyzing. The first band is going to be the GPS band, and that is going to have a lower frequency of 1.56 and an upper frequency of 1.58. That's going to be gigahertz, and the efficiency threshold or target that I'm shooting for is -2 dB. I'll add a second band for the Bluetooth, and this is going to start out at 2.4 and it's going to go up to 2.48 gigahertz, and this time we're looking for a -0.5 dB. With that, I have those two bands specified. I'll then want to define the topology, and this is where the power of Optenni comes in, or at least the convenience of Optenni, and we're going to allow Optenni to automatically determine our topology, and we're going to tell it that we'd like it to use 3 different components while it's looking. If I had a component supplier or a component manufacturer who I was purchasing these components from, I could go into my component library and tell Optenni specifically which component values I want it to consider, but I'm going to just skip that for the time being, and I'm going to click OK. What this is going to do is Optenni then evaluated the input data, evaluated the frequencies and the thresholds that I was looking for, and it generated the matching network that provided the best match given the inputs that I provided. So here, this is the topology where we have an inductor and a capacitor in series, and then another inductor in parallel with the load, and this is the match that it provides. This isn't quite as good as what we would like to see, so we're going to rerun that analysis, but this time we're going to increase the topology so that way there are 4 components being considered. This will take slightly longer, but still very quick. And now we're seeing a much better match in the GPS band and the Bluetooth band. So let me just go ahead and change the scaling so we can better see the data and the match. And we'll hide the efficiency data. So here we have the S parameters, and indeed we are getting a very good match in the Bluetooth band and the GPS band, and this is the topology that is providing that. So here we have our capacitor and inductor in parallel, and then we have a tank that is connecting it to the load. These are also the component values that Optenni was using, and if we wanted to look at other topologies, well then Optenni returns the 10 best topologies that generated the match that we were looking for, and we can see that the one on top is certainly the best and the one that we want to go with. So now that we have the matching network topology identified, we want to physically lay it out. So if we're using a tool from Cadence or Mentor Graphics, we can go back into that tool and we can physically lay out the matching network. We can also do this within XF, and that may take 5 or 10 minutes just to create these copper traces and add the vias. And then once we have this, we're going to want to run another simulation and verify that we get the same match from the physical layout as what Optenni was predicting. And often what we'll see here is shown in the graph is that the schematic is representing a very nice match in the GPS and the Bluetooth band, and that's shown by the dark blue line. But then once you physically lay it out and you either take measurements on a prototype or you run an FDTD simulation, you're going to see that the physical layout doesn't provide the same match. And that's because Optenni is not accounting for the full field interactions affecting that matching network. If you look at the schematic, you can see that the load, for example, is just treated as an impedance block. But if we look at the physical layout, we can see that the antenna is actually near the matching network. And if we look at the fields, we're going to see that there is quite a strong interaction between the antenna and between the matching network. And Optenni is not able to account for that. And so that's why we're seeing the difference between what the XFdtd simulation would generate and what the schematic would generate. So again, let's go back to the software and have a look. Let me open a second project. This one has the matching network layout included. Here we can see that layout, connecting the antenna down to these vias and into ground. This layout was actually laid out in XF, so here we've added an assembly and multiple parts representing each one of the pads and the copper traces. This took me maybe 10-15 minutes to create. I just created one, copy and pasted to create the rest, and then specified their orientation, which allowed me to move them into place. Once the physical geometry was in place in XF, I also needed to add the circuit components. And so here, let me compare them to what we have in Optenni. We can see that we have the same layout between XF and between Optenni. Here, the capacitor or the inductor are connected. Here's our capacitor and inductor that are connected, the tank circuit, and the antenna representing the load. Each of these components is taken on the same value that Optenni's predicted. And so what I want to do is run a simulation to see how the results line up. And again, that would be coming in and creating another XFdtd simulation, requesting S parameters, computing efficiency. And then when we load the results, we can come in and see the results that we got from the XFdtd simulation. Now, I already have that graph loaded. So let me just go ahead and show you here that we have the unmatched antenna in green. We have what Optenni predicted. So this is what the schematic displayed. And then if I show what actually happened from the XFdtd simulation, we can see that there's that difference in what was simulated. And again, that comes from Optenni treating the antenna as just an impedance block and not accounting for this field interaction. So if I want to understand that, I can save steady state fields and look at the field interaction between the antenna and the matching network. And so this shows me that there is indeed some coupling. We have the active antenna here. We can see the energy as it travels across the matching network and interacts with the matching network, and how the antenna is coupled onto the ground plane and is affecting that matching network. So when we compare this actual full wave result from the XFdtd simulation, we can see that there's more complex interactions going on here than what is captured by the simple schematic. So that takes us into our last step of the workflow, which is going to be determining the final component values to plug into this physical layout. So here we have the table on the left, which is showing the Optenni values. We have used full wave circuit matching optimization to figure out a different set or an optimal set of component values. And when we plug those two different values in, run a simulation, well, then we get the graph on the right. And if we use the Optenni values, we'll see that red line, which we've seen previously, but then this blue line is what we're going to get if we plug in the full wave MCO values. So to talk more about full wave matching circuit optimization, I've pulled an additional slide together just to show the workflow and kind of how it works or what the algorithm does. And so full wave matching circuit optimization has two steps. There's the first step where we run the response matrix. So this is where we run XFdtd simulations and we characterize the space. We figure out what is the coupling within the matching network, between the matching network and the antenna, and any other types of interactions that may be happening. And this is happening in the full wave 3D solver. Once this response matrix is finished running, Well, then it's time to take that and input it into a circuit optimization. So the user defines what they want to optimize on. So in this case, we are optimizing for S parameters. We wanted the GPS to be better than a 4 dB match, and we wanted the Bluetooth to be better than a 10 dB match. I could have optimized on efficiency if I wanted, but I used S parameters. And then also part of the circuit optimization is I provide the allowable circuit components. So I wanted capacitors to be chosen between 0 and 10 picofarads and inductors to be chosen between 0 and 10 nanohenries. Once we run that optimization, we figure out what is the optimal value, and that's what the output is. So the output tells us what are the values of these 4 components in order to meet the S parameter threshold that we defined. So in the application, there's not much to do here other than run that response matrix and do the optimization. In terms of the project and the setup, everything remains the same. We have our geometry, we have the physical layout, we have the circuit components defined, and we have everything here set up and ready to go. When we come into creating a simulation, instead of creating an XFdtd simulation, this is where we want to create a response matrix. So this is that first step where we run full wave 3D XFdtd simulations in order to characterize the space. We can send them to a cluster and utilize GPU resources. Once this is finished, well, then we move on to the circuit optimization. And this is where we define those S parameter goals and we provide the allowable circuit component values. And this is, once this simulation is finished or this optimization is finished, it returns the chosen component values. So we look in our results browser, we have the circuit optimization, we have the optimized component values. So here they are returned just as we've seen on the slides. And if I look at the S parameters, I can look at what the prediction was from full wave MCO. So it's predicted this match in the Bluetooth and this match here, this match in the GPS and this match in the Bluetooth. If we take these values and we apply them to the project, we can then run another simulation, just as we did with Optenni, and then we can get the actual, we can get the actual values here, and so we can see that there is a very good agreement between the prediction from full wave MCO and then the actual XFdtd simulation. So that's going to wrap up the workflow. We have gone from importing or creating an antenna, an unmatched antenna within XF. We then analyzed it to get S parameters and efficiency. Once we had that unmatched antenna characterized, we then exported that data into Optenni Lab, where we were able to synthesize a matching network topology. Once we had that topology, we were able to physically lay it out, and then we used full wave matching circuit optimization to figure out what those final optimal circuit component values should be in order to get the match that we're looking for in the 2 bands of operation. If you'd like to stick around for the Q&A portion, please do. Otherwise, thank you for attending. I hope that you have a better understanding of what the workflow is within XFdtd, and please contact us if you have any questions about anything you've seen or anything related to our products. Thank you.